So we are going to discuss magnitude comparator. So it is a type of combinational circuit which is going to compare the two binary numbers, and it will produce three output as which is greater, which is smaller, and which is equal value. Suppose if I take A and B as two input, means it will produce the three output as A greater than B, A less than B, and A equal to B. So this is the block diagram of a magnitude comparator. So as we discussed earlier, it accepts two inputs. It is going to compare the two binary numbers A and B, and it will produce whether A is greater than B, A equal to B, and A less than B as output. So coming to the 1-bit magnitude comparator, so the name itself implies A and B is having only one bit in their inputs, and it will produce the output as A equal to B, A less than B, and A greater than B as per the relative magnitude of the given binary numbers. So consider the truth table. It is having four possible combinations. Why? Because A and B is having only one bit. So A is having one bit and B is having one bit. Total we have 2 bits. So 2 power 2, 4. So 4 possible combinations in this truth table: 0, 0, 0, 1, 1, 0 and 1, 1. So if we take A and B value as 0, 0, means here both the value A and B are having the same value 0. So it will produce the output as A equal to B as high output 1. So remaining A less than B, A greater than B possess 0. So next case 0, 1. So here in the next case, A is having 0 value and B is having 1 value. So B value is greater. So in this output, A greater than A less than B produce 1, and the remaining values possess 0. And in the next case 1, 0, A is having high value and B is having low value. So A greater than B possess high output 1, and the remaining values A less than B, A equal to B is having 0 value. So in the last case of the truth table 1-bit magnitude comparator, 1, 1. So here in the A and B possess the same value 1. So A equal to B is produce the result 1. Remaining output produce the result as 0. So what is the logic of magnitude comparator? Which is going to compare whatever input we have given in the input side. It is going to compare the relative magnitude of the binary numbers, and it will produce the output A greater than B, whether it is greater than another number or equal to the number or equal less than the same number. So in the next 2-bit magnitude comparator, so the name itself implies A is having 2 bits and B is having 2 bits. A is having the 2 bits A1 and A0. B is having 2 bits B1 and B0. So it will produce the output A greater than B, A equal to B, and A less than B. So total we have 4 bits A1, A0, B1, B0. So what is 2 power 4? 16. So 16 possible combinations in the truth table of 2-bit magnitude comparator. So the first case of 2-bit magnitude comparator is all the inputs are 0. Here A1, A0 0, B1, B0 also 0. So both A and B possess the value 0. So since it is equal value, it is going to produce the result A equal to B as high output. Remaining outputs A less than B and A greater than b possess the value 0. So in the next case 0 0 0 1, so a 0 0 represents the bit 0 and 0 1 represents the bit 1. So since b is having 1 and a is having 0, a less than b produce 1. Remaining output will having the value 0. So in the next case 0 0 1 0, a1 a naught represents the value 0 and b1 b naught represents the value 2. So b is having the value 2 and a is having the bit 0. So since it is having higher value in b, it will produce a less than b value as high output 1. Remaining output is having the value 0. In the next case 0 0 1 1, a is having 0 and b represents the bit 3. So a represents the bit 0 and b represents the bit 3. So here also we'll have the same output 1. A less than b is having 1. Why? Because a is having only 0 value and b is having 3 value, bit 3. So a less than b possess the value 1. Remaining all the outputs are having the value 0. In the next case 0 1 0 0, so 0 1 represents the bit a1 a naught, it represents 1 and 0 0 represents the bit 0. So a is having high value. Since a is having high value, a greater than b is having 1. A greater than b produce 1 output. Remaining all the outputs a equal to b and a less than b possess value 0. So in the next case 0 1 0 1, so both the a value and b value are equal. So a is equal to b bit produces 1. Remaining a less than b and a greater than b produce the result 0. And in the next case 0 1 1 0, so a possesses the value 1 and b possesses the value 2. So it will produce the value a less than b as high output. Remaining output produces 0. The next bit 0 1 1 1, so 0 1 represents 1 and 1 1 represents the bit 3. So a less than b is having the value 1. The remaining bit is having the value 0. In the next case 1 0 0 0, a possesses the value 1 and b possesses the value 0. So it will produce the result as a greater than b value as 1. Remaining output produce the value 0. In the next case 1 0 0 1, a represents the bit 1 and b represents the bit 1. A represents the bit 2 and b represents the bit 1. So it will produce a greater than b value as 1. And in the next bit 1 0 1 0, both a and b are having the value same value. So it will produce a equal to b value as 1. Remaining two outputs are having the value 0. And in the next case 1 0 1 0, 1 0 1 1, so a is having 1 and b is having 3. So it will produce a less than b value as 1. And in the next case 1 1 0 0, a is having 3 and b is having 0. So a greater than b produces 1. Remaining output produces 0. And in the next case 1 1 0 1, A represents the bit 3 and B represents the bit 1. So A greater than B produces 1, remaining bits output produces 0. And in the next case 1110, A represents the value bit 3 and B represents the value bit 2. So A greater than B produces 1. The last case 1111, A and B is having the same value, equal value. So A is equal to B produces the output 1 and the remaining A less than B, A greater than B produces the output 0. And this is the output of K map of A greater than B. From the truth table of 2-bit magnitude comparator, we have designed this, and this is the came up for the output E equal to B. So whatever value getting A is equal to B output high value, so I'm just going to plot the high values in the K map. And next case came up for output A less than B. So the advantages of comparator. So comparators can be used in fast decision making circuits, and then we can use the comparator circuits in processor and ALU units. So the disadvantages of comparator, when we take small bits means the circuit will be simpler. When you are going to take for large bits, the circuit will be complex, and power consumption, it needs more power consumption. So the applications of magnitude comparator, it can be used in digital systems and decision making devices and central processing units and microcontrollers. Thank you.